Ok, también podemos hacer eso. Podemos empezar en inglés para que sea también más eficiente. Si surgen dudas y dicen, no, sabes que estoy perdida con la presentación, yo puedo venir a interpretar, no hay ningún tipo de problema.
Hola. Buenos días. Mucho gusto. That's all the Spanish I know for today. Hi, my name is Sumit. I am a Customer Success Engineering Manager at MathWorks. A little bit about me. I have been at MathWorks about 17 years. I have a background in electrical engineering. I have gotten myself into trouble with a lot of different technologies, image processing, computer vision, data analysis, high performance computing, and one of my favorites, modeling and simulation and embedded systems. So for today, I'm going to focus on talking about simulation, specifically the value of simulation. This is one of the topics that I have been working on quite a lot in the last few years along at different universities. So I actually have the opportunity to work with a lot of universities in the western part of United States. I come from California.
Get closer to the mic.
How about this? All right. I had to bend down as well. Okay. And I have the opportunity to connect with universities and research institutions in Latin America as well through Gabby. So thank you for that. And this time I thought, okay, I have an opportunity to come to Colombia and meet with the MATLAB and Simulink users or potential users in person. So I took that opportunity and here I am. Before I get started, a few questions. How many of you are actually doing simulation in any form or kind? Okay. Few of you, all right. Why do you like simulation? What is the value of simulation in your opinion? Anyone?
That I don't have to buy all the things, all the components, and then try to go to the lab and make the experiment. So I have first the facility to, well, not to buy the things, and second to automate the process to like get all list of values to make a faster evaluation and analysis.
Beautiful. So you save time and money by not having to buy things, and then you can speed up your design process.
Yeah.
Beautifully said. Who else?
Yeah, I want to. I'm not doing actually a simulation, but I want to learn fluid dynamic simulations, and I want to learn from that field. So that's my expertise in MATLAB.
Thermodynamic simulation.
Okay.
Very nice.
Fluid dynamics.
Very cool. Thank you. Who else would like to share?
I consider that one of the important points of simulation is that it allows for all the teams that work in a company to have faster and a clearer communication together. So I don't know, if team A has the simulation of the product, they can fastly send it to the team B and they can work on that like simultaneously.
Beautiful. So collaboration between teams, and then you can do faster simulation. You can exchange idea between teams faster in the industry.
Of course, and also not also between teams in a company, but also like in global communication. So if you have something here in Colombia, you can also share it with the United States, for example, and you could create a real good benefit from that.
Absolutely. All the design teams, manufacturing has become a global process now. So the teams are spread out all over the world. Using simulation, you can easily communicate design ideas and components with each other, and then build up whatever product you're building.
Of course.
Very nice. All of you, like you covered a lot of the reasons why people do simulation. Saving time, saving money, and better collaboration, faster development of products. All of those exactly why people use simulation in the industry. So my goal today is to give you some examples of how simulation is being done in the industry, in academia, so that potentially can give you ideas on how you can use more simulation in your project work, in your curriculum work, and then also get ready for potentially your future. If you go to the industry or you do research, or you stay in academia, that will give you some ideas. And at the end of the day, if I can get even one of you to do a little bit more simulation after today, after the session today, in any shape or form, in any tool, any software, I think that will be successful for me. Okay. So with that, let's jump into the talk. A few things. I will be showing you a lot of different things. But don't worry, I'm going to send you the slides as well. I think that the page that you shared already has the slides there, and you can click on the links and download the model and files and all of those things, and so you can explore them on your own time. But what I'm hoping for the next hour or so, that this can be a discussion. So feel free to ask questions. The best way to get information out of me is by asking questions. So please don't hesitate. Sound good?
And just to add, if you need to ask a question in Spanish, I can also help translate if you feel more comfortable that way. So totally fine.
Sound good? Alrighty. Beautiful. So before I get into simulation and the world of simulation and showing you examples, and one thing I want to point out is something to keep in mind is simulation has been around for a long time in different ways and forms. So simulation can be building a small model, like a wood model of an aircraft, or it could be like deriving some mathematical equations by hand to represent a system or a process. What is different now is actually digital transformation. With the rapid evolution of technology, both hardware and software, it is becoming possible to simulate a lot of different types of things that were not possible to simulate in the past. And the value, and because of that, the value of simulation is going up even more. So it is very important, if you're able to do it while you're in school, think about how you can use simulation in different parts of your curriculum work or your research work, so you're better prepared. And here are some like quick examples of simulation. Like a very simple example here is like a doorbell. Like a doorbell used to be just a small button like that in the past, or a knocker, and now you have a smart doorbell that you can look at, which is a camera and a microphone, and then you can look at who's at the door, and you don't even have to be home in order to communicate with somebody who is knocking on your door. Now, getting a bit more serious, if you're looking at some examples from the industry, so this is an example of how digital transformation is impacting the industry. So this is an example of triplex pump, which is used in oil and gas industry for pumping oil from the ground, and then or transferring oil between different containers. And okay, it's a triplex pump, but how is digital transformation helping? Well, nowadays in the industry, you create digital twins of heavy equipment like this, so that you can not only simulate the behavior of the pump, for example, how will it behave under different load conditions, how is it going to behave if there are faults and so on. You can simulate faults, but you can also use go beyond just the physical model of the pump and go towards in the world of AI and machine learning. So you can actually look at the signals or coming from the different sensors on a pump and predict when the pump will need maintenance. So if you're able to predict when the pump needs maintenance, so you can actually fix things in the pump before it breaks down. And if the pump is up and running all the time, you're saving time, you're saving money. Digital transformation is heavily impacting academia as well. And I guess we got a big boost 4 years ago during the pandemic, when suddenly everything had to go remote, and that impacted rapid development in the area of hybrid classrooms, online classes, and so on, and which led to the development of things like, okay, so we have virtual books, we have virtual projects and simulated projects. So a lot of those things coming into academia as well. So just to get started, so now coming back to simulations, so why run simulations? And you all shared some really good ideas, and to kind of combine all of them. So here are some of the reasons why simulations are used a lot in the industry. So one of the reasons is can be that the system is too big. Let's say, for example, we have a cruise ship like this, and you want to decide what type of generator you want to have on the ship so that it can meet all the power requirements for moving the ship, for keeping the lights on and having the appliances on, having the pool heated on on the cruise ship. Power requirements are needed, right? So the designers of a cruise ship now want to explore what type of generator they want to put in the ship. But they don't necessarily take out different generators and put them back in and out to see which generator works. It will take months of time, and it will slow things down. So that's where simulation comes in. So you have a simulation model of the ship, or you have maybe the simulation model of the power load, and then you try out different pump designs or generator designs to see which one will meet the power requirements. Another example is maybe the conditions are too difficult to replicate in real world. For example, here's an example of a aircraft carrier. So aircraft carrier has aircrafts and helicopters and all that, and then you have a hangar or a parking system for the aircrafts on the carrier, and you want to see if the parking system or the landing system for helicopters works in stormy conditions. So how will you do it? You're not going to take the aircraft carrier in the middle of a storm to see if the parking system works. So that's when simulation comes in. So you can simulate different types of conditions and then see whether the system that you're designing works under those different conditions, especially extreme conditions like this. And sometimes you get only one chance. Let's say you're sending a rover to another planet. NASA is sending a rover to Mars. You don't want to just send it and see if it lands or not. You wouldn't even know for hours whether it landed or not. So that's again simulation comes in. So you design everything from bottom up, the physical model of the aircraft, the guidance and navigation system, the landing system, everything is simulated a lot over multiple years. So that's where simulation, some of the reasons why simulation is very important. Now, okay, I have links here so you can explore these stories. These are actually stories from MathWorks customers. So you can learn about how they use MATLAB and Simulink for their work. The question is, how do they do it? So I'm going to show you a very, very short example, a teaser of how you can explore kind of an industrial simulation system like this on your own right now, if you want. So I'm just going to bring up the example that Gabby was showing earlier on electrification. So electrification is a huge area right now, a huge discipline right now, or a domain because of climate change related challenges that Gabby brought up. And in general, we are seeing that electrification is actually good for the climate, and it's actually good from the perspective of cost and efficiency as well, as the technology is improving, like battery technology is improving. So this is an example of the windmill that Gabby brought up. So how is simulation helping in a case like this? So Gabby already showed the video, so I'm not going to spend time on the video, but I'll point out two things here and then show you the model running to see what it looks like. So the two aspects to simulating a windmill like this. One of them is actual physical design, which means not only just the graphics, but also the inertial design and of the components like weight and all of that, and the design of the angle of the shape of the blades, the pitch angle, and those kind of things, and then the generator inside it, and then the control aspect of it. So simulation is used across the board in all of this. So in this case, for example, I'll show you. Okay, let me pull up the demo itself. Yep. So this is the Simulink model of the wind turbine. And let me just hit the run button. So you know that it actually works. And I can show you a few things internally, and I'll show you where to find the file. So you can play with it on your own. And you can create some cool conditions. Let's say if the gravity is 11.1 instead of 9.8, or if you want to see what happens if the wind speed is 100 miles an hour, you can simulate all of those things and play with it. So the simulation is starting up. I mean, the simulation calculation has already been done, and now the visualization is running, so you can see what it will potentially look like in real world. So in the beginning, the windmill was not moving, the turbine was static, and then it started up because there's wind, simulated wind. Yeah, seems to be working fine. So what is actually happening under the hood? So a few things I'll point out. So first of all, the 3D model of the wind turbine itself, the blades, the nacelle, the base, all of those were created in SolidWorks. So SolidWorks is a great tool for 3D design like this. You can design both the physical properties and initial properties, the visualization, all of that. Then you bring it, then import it into MATLAB. Actually, you import it into Simulink. I thought a lot of you are familiar with MATLAB, like Simulink and Simscape and those tools, right? In case you're not familiar, so we have kind of two product lines. One of them is MATLAB and the toolboxes, which are more for programming, and then you saw apps that Gabby showed. So and it's more for like data analysis type workflows. Simulink and the block sets, they are more for system level design like this. And Simulink is actually used heavily in aerospace, automotive industries, and so on. So pretty much any aircraft you see flying around, or any car you see, that has been, at some part of it has been designed using Simulink. So Simulink, in the Simulink, you create models like this. There's a Simulink model which is composed like a block diagram, and then you can actually click on the blocks and see what's inside the blocks as well. So as I was saying, we created 3D model of the wind turbine in SolidWorks, imported it into Simulink, and when it comes into Simulink, this is what it looks like. So this is the model of the wind of the blades. This is the model of the nacelle to which the blades are connected with the generator and everything, and so on. You can double click on it. You can go inside. You can keep, so the 3 blades. You can go inside blade 1, and you can. You have the inertial properties here. You can. There's a pin here that is connecting the blade to the turbine. You can look at the geometry. This is what the geometry looks like. So all the way down to the lowest level of detail of the design of the blade. So this is how you design things in a 3D in a modeling environment. Bring it into Simulink, and then you provide actuation to it. You have a 3D body, you provide force to it or actuation, it will move. And then you design a controller so that the movement is in a controlled fashion. So that is what is going on here. So you're applying wind. That block represents wind, that is the actuation into the system. And then you have a controller that is going to control the motion of the turbine. So everything is in right here. And when I click on the run button, it does the simulation over a set period of time, and then shows you the simulation, the visualization. What happens after this? How do you go from this simulation model to real world? Now, there are 2 aspects to it, going to the real world. One aspect is the turbine itself. That's when you get into the phase of prototyping the turbine, like you manufacture the turbine or do some prototyping and build the physical thing. And the second part is actually the intelligence, the controller. the controller intelligence or the control model is actually automatically converted from Simulink to C code or HDL code that is going to go and sit on the controller on the turbine. And this is how, and it's a fairly easy process. So right click and then say C++ code or HDL code, PLC code. You can decide what language you want to go to based on the embedded system or the hardware that you have on the nacelle and the turbine. So this is the industrial workflow. Now the advantage of this, well, like we discussed, is saving time, saving money at the end of the day, because you don't have to. You can prototype and try out a lot of designs in simulation model itself, like the size of the wind vane and the shape of the vane, like the size of the turbine, how much power is generating, and then testing different like wind conditions and all that. You can do all that testing in simulation mode before you start building anything. And this is how the industry saves millions of dollars. And this is exactly how, I mean, I showed you an example of a wind turbine here. This is how cars are made. This is how aircrafts are built. This is what is going on in the industry. And even like if you're getting into like medical robotics and so on, that's how it is done. Now, I gave you examples of heavy industries, but what about more soft industries like finance and so on? It's the same idea. So in finance, you will model maybe Black-Scholes equation, and then start using like AI techniques and so on in terms of optimizing, for example, your investment ideas and testing and so on. So that's another type of simulation. Maybe you're simulating the market, for example. So that's the idea, all right?
There's a question there. Ya le llevo.
Is possible to import other kind of files for the three-dimensional model? You mentioned SolidWorks. Is possible to import of other software like Autodesk Inventor?
Yes. So the question is, I talked about the interface with SolidWorks, but what about other 3D modeling tools? Yes. So our product is called Simscape. Simscape Multibody. And if you look at the documentation for that, then you will see other tools that we support. So we do support Autodesk. Which one?
Step files.
STL files.
Step
files. I'm not sure about that. But then we have other tools like Onshape. Those are supported. Yeah.
Thank you.
I want to know if it's a workflow that we can include in order to make like hardware in the loop with the same structure, like digital twin, something like that, but directly in Simulink.
Oh, yes. So the question is, can Simulink do hardware in loop, software in loop, those types of workflows? Absolutely, yes. And that's exactly, so Simulink is an industrial tool. So we actually support that at an industrial level. Like MATLAB and Simulink working with things like even DSpace and so on. And I think somebody mentioned SpeedGoat hardware earlier today. So that is our dedicated like hardware for hardware in loop simulation as well. So 100% yes. And in fact, I'll show you how you can bring that workflow to the classroom, to your projects, even using Arduino, for example. Right. So in case you're curious, where can you find the files for this? Just go to mathworks.com, and I believe this should work. Wind turbine. Wind turbine model. There you go. Just feel free to go ahead and download it and play with it. It's in File Exchange. Gabby already showed you File Exchange, so I'll not get into the details, but there you go. And it's supported in different versions of MATLAB as well. Okay, moving on.
This about how you can predict by simulation some windy change, some windy change like not wind, only sun, or some changes in the fluid of the air. Can you show the answers for that with a geographic specification?
Yes. So the question is, how do you simulate climate conditions or atmosphere conditions like humidity, wind speed, temperature, things like that, right? Yes. So that's a great question. And here's the thing. All of those can be simulated right here. So right now, so you see this block, say turbine input wind. So this is mostly about wind speed and so on that we are simulating. But then what you can do is you can add other climate conditions here where you can simulate temperature, humidity, and so on. Because think about it, when temperature and humidity come in, when wind, that is going to change the density of air, and it's going to change maybe the temperature and so on. So you can add more complications or more advanced features to this model itself to simulate those conditions. Okay, so the question was, how can you include conditions like temperature, humidity, and so on in the model? I just said this is a block for wind speed. You can add other things in the same model. Yes, please.
Ok, sí, sí hay maneras de incorporar ese tipo como de entradas. Incluso hay ese bloque lo que incluye es la velocidad del viento como entrada. Incluso, Subit, no sé si lo quieres, sorry, Subit, do you want to open the blog, like the actual, eso? Entonces ahí están las entradas, ¿sí? De la velocidad del viento y de la dirección del viento.
So after giving that answer, have another question. It's like, yeah, that's the condition in one place on one geographic place, but can you find a different aspects of one in one part of the world? It's like, yeah, I want to put an air propeller in Africa, for example. That's not the same aspects you show in this graph. So can you have that information to simulate with that different aspects?
So I guess I'm hearing two questions there. So one of them being, can you simulate the behavior or the model in different parts of the world? And secondly, can you get like weather condition information in those parts of as well? Yes. So the weather condition information is available for free online. If you go to website like NOAA, or other websites, you will be able to find weather conditions in different parts of the world at any point of time, like from a weather website. In terms of simulating and analyzing the performance of a wind turbine in different locations, so that's how you can do it. So you just collect the weather information and then put the conditions in the Simulink model. And just to extend that, so that's exactly how energy engineers or wind turbine engineers or energy companies, they determine where to install wind turbines, because you don't want to install a wind turbine when there's no wind. So that is how they actually, by the use of simulation models like this and information about weather and weather patterns and wind patterns in different parts of the country or the world, they figure out what is the most optimal place to install a wind farm. So that's how it is done in simulation. Good. All right. So moving on. So yeah. So where was I? Okay, I'll go ahead and close this model for now. We don't need this. Yeah, I showed you where to find the model. Okay, now let's come to academia. So this is how simulation is being used in industry. But what about academia? I'll show you two ways of doing it. One of them being, say, advanced projects, and then classroom projects. Okay, so let's talk about some advanced projects. And an example of an advanced project is potentially like a student competition team. So this is the story from Formula Student. And this competition, the story I have is from about 4 or 5 years ago. And in Formula Student, teams are designing small scale racing cars. So I'm showing you a part of the story, not the whole story. You can learn more about it on mathworks.com. So one of the challenges is, one of the very fundamental challenges is to evaluate different designs for the car that they're planning on building. And a lot of design decisions have to be made, that what size of the battery, engine, and what size of motor, the location of the components, because location of these components, like batteries and those things, are quite heavy. So it will change the center of gravity of the car and change the dynamics of the car. And then if and when and how to, what type of aerodynamics package to install, that is going to again impact the performance of the car, the efficiency, range, and so on. The suspension geometry, whether you want to soft, hard suspension, high, low, all of those kind of things. But the thing is, there are lots and lots of options just in these. But the time is actually very limited, because this is typically a 6 or 7 or maybe a 10-month project, and it starts in October and ends in August. But that does not mean that you actually have the entire 8 or 9 months to come up with a design, because the rollout of the design has to happen like 2 or 3 months before the end of the competition. That's when the judges start testing, or you start testing and comparing it to other teams. Design freeze has to happen before that. And by rollout, I actually mean making the car and start driving it. Design freeze has to happen before that, 2 or 3 months before that. So you can actually start building the car. So you only have 2 or 3 months realistically to come up with a design and make those design decisions. So that's the thing. So that's why the time is actually limited. So this is where simulation helps. So one of the teams was using MATLAB Simulink, our tool chain for the competition, and they used simulation a lot. And they use simulation for both aspects. One of them being designing the car itself, and then evaluating the performance of the car by driving it around in a virtual test track as well. So they simulated everything, all the way from the car as well as the driving conditions, like the type of the road, like less grip, high grip, temperature, and things like that. What is this? Yeah. So their simulation model, this is how they were testing some of the things out that we were just talking about. So they built in some redundancies and change options, so they could try out different types of powertrains, different types of batteries, and then different locations for the batteries in the car to test out the center of gravity and all of those things, and then they set up different configurations by using automated scripts. And it's not that they were going and clicking and evaluating the different designs one by one. They just set up a script and then they automatically change the different design parameters, use parallel computing to run parallel simulations, and then come up with an optimal design in a matter of a few months. And then they start building the car, and then they start testing later on. Okay. Now let's keep bringing this closer. So what can we do today? So this is where one of the ideas that I'll bring up is, think about how you can use simulation in your labs, in the lab projects or your curriculum projects, or any advanced project you're doing in the final year, for example, like 6-month project, 12-month project, and so on. Now, so this is what a typical lab workflow looks like. And I'm showing you this because what I'm going to try to do is replicate the exact workflow in the world of simulation. and tell me if this makes sense or if or not. The typical lab workflow, you start with the concept that this is what I want to do. This is what I want to try out. Then you may go towards studying the theory behind it and maybe deriving mathematical equations in order to understand the mathematics behind that concept. Then you might do some small experiments like virtually, okay, let me write this piece of code, or let me click on, let me write a blink LED example on an Arduino board and see if things are working. Then you start building things, either a full software project or you do a smaller or go towards a hardware project. Then you report things out. And then the cycle repeats. You do this for one project, you change the semester, you work on another project, and you do the same thing. Does this make sense? Is the workflow more or less? Okay. So let me show you how you can replicate this workflow in the world of simulation. So I'm going to talk about three different workflows at a high level, like a full virtual lab model, a hardware at home or a low-cost hardware model using, say, cell phones or Arduino and so on, and then maybe even remotely accessed hardware. And actually, I created these slides around 21, 22 when pandemic was at peak, and a lot of there was a lot of interest in going towards hybrid classrooms, online classrooms. But I think everything that we learned it actually made us stronger. So we can do new things now. We can still use these approaches. So let me show you a few examples of that. Now, one thing to keep in mind is that some of the things we have been talking about, or things that you shared about the value of simulation, these can actually help you gain experience with all of those, like how to keep costs down, how to replicate realism, complexity, collaboration. Somebody talked about collaboration and experience, industrial workflows. All of those things can be addressed with these workflows or these examples. So let me go through a few examples real quick, and then we can open the floor for questions and discussion. But any questions so far? Okay. Wait.
Is this simulation platform? Is the simulation platform like able to do simulations of fluids? I mean, like if we're interested in doing a simulation, for example, of the sea or the flow of the water in the sea, is that able to do it?
So the question is, does the simulation tool allow you to do simulation of water flow, right?
Yeah.
Are you going towards more like finite element modeling or no?
Yes, similar to that.
Okay. Yeah. So MATLAB is not the finite element modeling is not one of our strong suites. So MATLAB and Simulink cannot do that well. But what we do is we actually can talk to other FEM tools. So you can set up your model in a different FEM tool, and then have MATLAB talk to that tool to do the high level analysis. But we can talk offline as well.
Sure. Thank you.
Cool. All right. Anything else before I jump into the example? Okay. So this is a virtual lab on RC circuits. Looks familiar? RC circuits? Yes? No? Yeah. So if you're from electrical engineering, this will look very familiar. This is a very fundamental circuit and especially even for charging, discharging circuits and so on. So this is a very fundamental circuit, and you will see this across the board. Like there are motors in a car, like wiper motors and like windshield, like window motors, everywhere. The RC circuit is absolutely fundamental, used everywhere. So let me show you like how you can use virtual labs to, if you're a professor, how you can use virtual labs to introduce the concept of RC circuits and reinforce concepts using these virtual labs. Or if you're a student, or if you want to just learn something on your own, how can you use simulation like this to gain understanding and build intuition about about these types of scenarios at low cost, and you don't have to buy things, and secondly, you don't blow things up, so you don't have to buy another set. So the approach here will be the same as before, like introduce the concept, explore the mathematics behind the circuit, explore it in a virtual lab, and then maybe do some further exploration as part of just trying things out or assignments, and then report everything out. So let's go take a look at this example. So I'm going to start with this live script. Gabby already showed you live script, so I'm not going to go into the details. I'll just walk through this. So this script is set up as potentially a project for maybe second year engineering circuits class. So you can see there's a table of contents, some introduction, learning objectives, all of those details are in here. And now, okay, let me clear everything out so you can see things happening. So this is where you share the learning objectives and introduction to share the concepts of our RC circuit. So this is a section where you can talk about some of those things, which are the first circle in that 5-circle flow. The second one is background theory. Start exploring the circuit, the mathematics behind that a little bit. Here, this is kind of equivalent of actually writing using a pen and paper and deriving some mathematical equations of the RC circuit. So how do we do that here? So in this case, okay, there's a diagram, and can you guys read it? I need to make it bigger. Maybe I'll zoom in a bit. Is this better? Okay. So this is the RC circuit. Mathematically, these are the equations that you can derive. Now let's see how we can explore this equation. If you're just doing in the classroom, the traditional way, we would be manually putting in the values of R and C and figuring out the response of the voltage and current and C, and then try to plot it and all that. In MATLAB, you can use a symbolic math toolbox to derive those equations symbolically, and then do some of those operation and exploration in the symbolic domain first. So I throw that in. MATLAB gives me this representation of current and voltage, just as we would derive from using pen and paper. Okay, there's some help available here. I don't need help right now. I'll give you guys a script. You can explore this, what it means on your own. Now, once we have that, then instead of again drawing the voltage and current over time using pen and paper, let's use the fplot command to do a function, the plot of the function itself, the entire function. This is what the voltage and current characteristic look like in this particular RC circuit. So once we have done some of the exploration, theoretical exploration in the symbolic domain, now let's become a little bit more practical and start by getting into the numeric domain. So I can convert those symbolic expressions to numeric equations using this command MATLAB function. And symbolic math toolbox will give me the numeric representation of those two expressions. I have that. Now I can start working in the numeric domain or proper like technology hardware domain, and let's plot it. Just like that. So now we have the numeric representation of the voltage and current response. Now here's the fun part. Now instead of sitting in a lab and trying out different values of resistance and capacitance and manually changing them and trying to build the intuition, now I can just say, okay, instead of a capacitance of 500 ohm or resistance 500 ohms, let's reduce it to 320. Now what does it look like? This is what it looks like. What if I increase the capacitance? What's going to happen then? This is what's going to happen. So this is how you can very easily replicate the behavior in a lab in a simulation world. Okay, let's go further. We are in the world of MATLAB, and we are working with a simple circuit like this, right? But what happens if the circuit becomes more complex? That's where Simulink starts coming in. So that is why Simulink is used in the industry. So we use Simulink to build up this block diagram model of the RC circuit. And let me just set up the initial starting values of voltage, current, and resistance, and so on. And then I will show you what the model looks like. Open the model. Oops. Why can't you find that? Yes, you will be able to find it. It's opening. There you go. This is the RC circuit, the Simulink model of the RC circuit. And as you can see, I have done a bunch of other things here as well. So this is the basic RC circuit, resistance and capacitance in series. And this is the switching circuit. If you go back up, this is the voltage source. I have a DC voltage source right now, the value defined in the MATLAB script earlier. But then I have some other exciting things going on here as well. But I'll come to that one by one. So now if we want to replicate the exact same behavior as earlier, so I have this command called plot capacitor voltage, which is, you can see at the bottom of the script here. It is going to run the Simulink model and create a plot for us. So this is how you can see I'm also wrapping up the simulation model in a MATLAB script. So MATLAB and Simulink talking to each other, a lot of things going on here. And so this is what the capacitor voltage looks like. I have a switching circuit just on and off. So that's what's going on here. Now, if I want to make things exciting, okay, so what happens if I attach a resistor in parallel to the capacitor? You can do that in the lab, right? So you just attach another resistor in parallel. You do the same thing in here, in Simulink. So I have this, R1 is already there. I have R2, but R2 is actually currently commented out. Let me uncomment it, save it, and then come back here and run this section. So earlier, the voltage went up to 10 volts, 0 to 10 volts in the capacitor. Now it goes between 0 and 5 because we attach the resistor in parallel. So this is how you can try out different hardware configurations and then play with it. And there's a lot of other things in the model as well, like going from a DC voltage source to an AC voltage source. All of those things are set up as well. And you can set it up as, this is actually, as I mentioned, set up as a project. So now you can, as a professor, you can give this file or a couple of files to students and ask them to fill out what they understood by trying out those things. So this is like how you can replicate a lab workflow. Any questions before I move on? Okay. Yes, I'm not going to go through this in detail. You already saw this. Just a reminder. We used 4 products here: MATLAB, Symbolic Math Toolbox, Simulink, and Simscape Electrical. Okay. Now let's bring some hardware into the picture. This is an approach too, like working with low-cost hardware or hardware at home, like using whatever hardware is available to you for running experiments, or using things like Arduino, Raspberry Pi, and so on. So this example actually deals with using or exploring deep learning with a smartphone. I'm assuming all of you have smartphones at this point of time. Yes. All right. Have you heard of MATLAB Mobile? MATLAB Mobile? Yes, yes. So this example actually uses MATLAB Mobile. So I won't be able to show you this example running right now, camera and screen and all that, but afterwards, if you want, I can show this to you running in MATLAB Mobile. So the approach here is, if you're thinking about using it in the class, so you can introduce theory in the class. You can download MATLAB Mobile on your iOS and Android device. Then in MATLAB Mobile, you can actually access the different sensors and on the device, like camera and gyroscope and all of those things. And you can even access pre-built deep learning networks like GoogleNet, for example. I've been using GoogleNet in this case. You can download, you can use GoogleNet to actually use your mobile phone to identify objects. There's a link here that will take you to the full demo. It's actually a published demo on mathworks.com. So pretty much this is how it works. So on your mobile phone, you create a mobile dev object. As you can see, it can talk to accelerometer, angular velocity, magnetic sensor, orientation sensor, position, GPS. It can talk to all of them. From there, you turn on the camera. Okay, I want to use the back camera. Then you say, okay, also download or access GoogleNet. It's a pretty standard neural network. Then you say, okay, take a snapshot manually. So you can actually point the phone at something, take a snapshot. And then change the size of the snapshot so that it meets the requirement of GoogleNet, 224 by 224 pixels in size. And use a classify method of the neural network to identify what the object is. So this is an example that uses like pre-built networks and so on, but this is a really easy way to start exploring the world of deep learning and so on, using low-cost hardware. If you want, I can show it to you in action on my phone afterwards. A couple of things here to keep in mind in case you haven't seen this. mathworks.com/hardware. So if you want to see all the hardware that is supported directly from MATLAB and Simulink, this is where you can find information. Let's talk a little bit about different workflows that are supported as well. So we support different types of workflows when working with hardware. Live data streaming. If you have a hardware like say Raspberry Pi and you have a camera connected to it, or you have sensors like temperature, vibration sensors connected to Arduino, if you want to acquire data live streaming, so that workflow is supported. Code generation and targeting workflows are supported, which means so in live data streaming, typically you need to have the hardware connected to your MATLAB session on a laptop, and you're capturing data into MATLAB directly. But if you want to have your hardware running in a standalone fashion, say you want to deploy an algorithm to the hardware and let it out in the world, That is typically the code generation and targeting workflow, and that is supported as well. So this is actually the workflow that is used most in the industry. So remember I was talking about programming the control system of the wind turbine. So this is the workflow that is used in the industry. The good thing is this workflow is supported even for Arduino Raspberry Pi low-cost hardware as well. So you can gain exposure to the workflows, industrial workflows using low-cost hardware. And of course, there's a lot of project specific like hardware that we support for project-based learning as well. To your question about code generation and hardware in the loop testing, yes. So this is where you can find more information about different types of hardware in the loop workflows that we support. How many of you are using Arduinos? It's a few of you. Okay. Are you using Arduino with MATLAB and Simulink? Yes. Do you use a parameter tuning capability? Have you used that?
Bueno, nosotros hicimos Arduinos con LEDs y también implementamos como para una IA, una inteligencia artificial basada a, más que todo para la, ¿cómo se llama eso? La implementación para las mascotas, como digamos la comida. Entonces queríamos que la IA hiciera eso, pero en el Arduino.
So they're using Arduinos with LEDs, and they're trying to develop an AI model to to automate the process of feeding their pets.
Okay.
So,
Nice. And how are they changing the parameters of the model? Are they changing the parameters and programming it all that over and over again? Is that what they're doing, or are they using the automatic monitor and tune capability?
si lo estás cambiando, modificando manualmente los parámetros, o si estás usando algún tipo de interfaz como para hacerlo de manera automática, como los ajustes.
O sea, en el programa utilizamos 4 interfaces diferentes, pero más o menos se manejaron más que todo con Python. Queríamos como implementarle también Python para que no fuera solamente un código pequeño con solo IA, sino que fuera un código grandísimo.
So they're using different interfaces like Arduino IDE. They're using Python as well as part of the process. So I don't think they're using that
Okay.
option.
So what I would recommend is try out this option. So you use Simulink and the Simulink support package for Arduino. This has 3 very important capabilities: connecting to the I/O devices, monitoring and tuning. So if you are designing your algorithm and then you need to change the parameters of the algorithm, you can do it on the fly. You do not have to code and compile and deploy, and you don't have to repeat that process. The Simulink model can actually stay connected to the algorithm on the hardware, and then whatever changes you make, a Simulink model will get reflected there. So this is actually an example of hardware and loop simulation, hardware and loop workflow. This is what is used in the industry as well. This can speed up your simulation process. Said a lot of things.
Okay. ¿Lo captaste o te lo trajo? She understood.
Beautiful. Yeah. So this is a very, very powerful capability that we have in our tool chain. So try it out. Any other questions before we move on? Okay. Right. The last thing is yes, question.
Is that tool able to identify the devices it's connected to, or do we have to specify it?
So the question is, how do you identify the devices that are connected, or do you have to specify the connection details?
Yes.
Yeah. So that's a good question. So when you download the support package that we have for say Arduino, Simulink support package, our tools will download Arduino IDE. It will download the MATLAB interface with Arduino IDE, and it will do the installation and everything automatically. So once that installation is done, then whenever you connect your Arduino board or maybe a Raspberry Pi board to the computer, and you start things up, the software up, it will automatically find it. And you can just from a drop down, you can select, okay, if you have 4 Arduinos connected, you can from a drop down select which one do you want to put on program and all that. So a lot of things is automatic is the short answer.
Okay, thank you.
Okay, so we saw two different approaches so far. One of them being fully virtual experiment or a project or a lab, and then we saw something in between, hardware and software together. This is an example of remotely accessed hardware. So in this particular case, this is a project, say, around traffic management and figuring out how many lanes of road are needed if based on historical traffic data in a particular location or particular road. So this is actually a very cool example. There's a lot of moving parts as well, so I'll try to explain them one by one. So what's happening here is, what we will do is we will acquire data generated by remote hardware that is already sitting on an IoT platform, and then analyze the data locally, and then do the recommendation of how many lanes are needed and so on. So that is the project. But the exciting part is also how is the data generated and put on an IoT platform. So let me show that to you. So this part is just about accessing data, analyzing data, and then providing recommendation on lanes and all that. But the exciting part is how is the data created as well. So I have included links in the file, so you can take a look at them later. And you can actually download the files from File Exchange as well. So what's happening is we actually have a camera connected to a Raspberry Pi board, and there's a Simulink model running on the Raspberry Pi board. It is looking at the road outside MathWorks head office in Boston and giving us live information about the traffic there. How many cars are going east, how many cars are going west. So Simulink model running on a Raspberry Pi board and then counting cars. That is what is going on. Where is the data? The data is being sent to ThingSpeak. ThingSpeak is our Internet of Things platform. So this is actually live information. So going west, there's no traffic, it's all green. Going east, there's some traffic. That's why this is yellow. If there's a traffic jam, it will be red. So this is, and then we have historical data for the traffic. Now we can actually, this data is being generated non-stop. And this is how, like, we're talking about weather data as well. So there are places where websites that are capturing weather data, and you can collect data from there. In fact, ThingSpeak itself. So you all have access to ThingSpeak, by the way. This is MathWorks platform for Internet of Things. I think, Gabby, you mentioned this briefly as well. No, you did not. Okay. So you all have access to ThingSpeak, IoT, if you want to do IoT. And there are lots of channels that you can explore. Yes. So what I'm going to do is I'm going to show you how you can interact with ThingSpeak a little bit, and then how you can pull data and then create a project out of it. So, and here are some ideas on how to make a group project out of it if you want to set up something like this. So maybe one of the students is maybe a 3-student project. One of the students is working on the car counting algorithm. Second one working on actually deploying it to hardware, and third one doing the data analysis and reporting. So this is the third part, data analysis and reporting. So in order to get data from ThingSpeak, you just use the command ThingSpeak read and provide it a channel number. So the channel number is this one, channel ID. So if I do that, if I run this piece of code, this will tell me right now what was the latest data that was pushed to ThingSpeak. So the camera saw in Boston that there were 9 cars going east and 18 cars going west. Okay, but this is not enough information. If I want to actually set up full algorithm, I need more information, like when was this timestamp, and maybe data for multiple data points. So that's where we can start adding more options to ThingSpeak Read to get data maybe in a timetable format and then read multiple data points. So here, for example, I'm reading, okay, let's take a look at the last 50 data points. This is what it looks like. So now that we have the last 50 data points, now we have traffic information, historical information. Now we can start using this information to design a traffic management system and then figure out, okay, how many lanes are needed. So I'm going to just stop here. I'm not going to go into the details, but yeah. So this is something that can be done as part of the project. So this is how my point being, you can set up a group project and that uses simulation, remote access hardware, and creates an opportunity for collaboration as well. Like 3 students can be sitting in 3 different places, working on 3 different aspects of the project and still collaborating on the same project. Am I making sense? All right. Now, so I showed you a few examples here. So there's more details here, ThingSpeak and so on. What I want to point out is we actually have a lot of examples of virtual labs already available to you. So if you go to mathworks.com, learn, let's say teach with MATLAB, courseware, see all courseware, and then filter by, okay, the labs are not here. Maybe go back. Courseware type, labs. This is where you'll find a lot of the things that we have, that MathWorks has created or professors around the world have created and shared that. So we already saw the climate data visualization app that Gabby you were showing. So that is available here. Introduction to engineering with Arduino. If you want to set up an entire course using Arduino, or you want to just explore, learn about Arduino, you can download this course or curriculum module. The wind turbine model is here. If you want to do some quadcopter modeling, there's a model of a quadcopter that you can download and start playing with the model and design control algorithms and so on for the quadcopter. Something even if you bring something maybe advanced model predictive control, virtual lab around that. If you're into controls, there was a cool one here. Another control, this is virtual hardware for control labs. So a table. So if you want to control the table so that the ball stays in a particular spot, there's a virtual model for that. So you can play with it. You don't have to buy the hardware and set it up in the lab. So I'll say, check out these labs. This will give you a lot of other ideas for virtual labs, simulation. Any questions?
I have a question. Simulink is a great software to simulate the dynamical process. But in the recent version, I find it's so difficult to configure the model. Which tutorial, which material I can check to establish a similar or something like that, MATLAB on RAM in Simulink, starting the base model to create a complicated model
Right.
in this kind of simulations.
Yes. So I think that the multiple parts to that question / comment. One of them, Simulink has become complicated, and the second one being, how do I get started with Simulink now? So I will acknowledge that, because I've been at MathWorks 17 years, and 17 years ago, Simulink was very different than what Simulink is today. And I will acknowledge that Simulink has become complicated, but it's a matter of like adding more capabilities, responding to what our customers are asking for. As I mentioned, Simulink is an industrial tool, so a lot of the requirements are coming from the industry that we need this, we need that, and a lot of that is being actually kind of driven by regulations as well, like FAA and automotive regulations. They increase requirements as well. So definitely a lot of capabilities have come in, and it can be overwhelming. So my suggestion will be to your question, and I think Gabby pointed this out earlier as well, like go to the self-paced online trainings that are available to you. And I think all of the self-paced online trainings are available to you because you have a campus-wide license. Yes, so let me zoom out a bit. Yeah, so I would suggest in the world of Simulink, okay, getting started with Simulink. So Simulink fundamentals, control design with Simulink, circuit simulation, Simscape. So this will get you started with the Simulink, and then designing control systems, and also Simscape will get you started with the world of Simscape. And then the circuits one as well. So I would suggest you get started with these, and then after you have done those, then go towards Simulink fundamentals. Simulink fundamentals is a deeper dive into the Simulink environment and modeling suggestions or the roadmap that you're talking about. And these are exactly the same trainings that we sell to our commercial customers as well, which is available to you as part of the license. So two aspects there. So when you are going through this, you will know exactly the same workflow as a commercial customer. So you'll use all the features, and then you can decide for your class or for your research work what you want to use, what you don't want to use. And the other aspect is, as a student, if you take these courses, you get certificates. Gabby was talking about the certificates. You can actually post a certificate on your LinkedIn profile, because it's the same training that we sell to commercial customers as well as in academia. So the certificate will get recognized in the industry as well. Any other questions?
So you tell what aspect is important to simulate with MATLAB or Simulink, but I have the question, what do you think about the other spaces of simulation like ROS or NVIDIA Isaac? It's like a competition, or you think it's complement one each other?
So the question is, what about other tools for modeling and simulation? Do we see those as competition? Do we see as complementary? So first of all, that's a great way to ask the question in an open-minded fashion. So I would say it's more complementary, because here's something to keep in mind, that when you're working on an industrial project, it is very difficult to actually complete the project with a single tool. So you need to use different tools for different parts of the project. Okay, so that's where, that's how our product line has been designed as well. So we provide a lot of capabilities in our products, but then we have handshaking capabilities with a lot of other software and hardware as well. So that you can use MathWorks products for parts of the solution, or you can use other tools for other parts of the solution, and then bring those two together. So it is important for you, while you're in school, to learn about different tools, and then also learn about how to make them talk to each other. Because when you go out in the industry, you will definitely come into a situation when you need to make different tools talk to each other. So that's a very important skill to learn, and try to learn that while you're in school here.
You're telling it's more complement than competition. Yeah, that's
exactly.
right. Thank you.
Yes. In short, yes.
I think we're fine. De todos modos, las diapositivas de Summit están en la misma página que les compartimos. Si a alguien le falta el QR, me puede levantar la manita y yo se los dejo ahí. Sí, pues para ir cerrando, agradecerles su atención y las preguntas. Siempre nos alegra mucho cuando hay preguntas y no sentimos que le estamos hablando al vacío. Y bueno, seguimos en contacto, cualquier cosa. Aquí estamos precisamente para apoyar a la universidad con diferentes tipos de iniciativas.
Thank you for hosting us here, and thank you to the university, and thank you to the Components team. And I guess we'll be here for a few more minutes if you have any questions or comments. And then other than that, thank you very much for joining us today.